Welcome to Brain Vision.
For this question, we are asked to consider two thin parallel wires separated by a distance of 13 centimeters carrying a current I of 35 amperes. So I said that the distance from point Q to R on our graph, where the two wires are at point R and point Q, and they're flowing into or out of the page, which is why they're represented by a dot, that distance is 0.13 meters. So I converted everything from centimeters to meters. Okay. It says determine the magnetic field vector at a point 10 centimeters from one wire and 6 centimeters from the other wire. So 10 centimeters from one wire and 6 centimeters from the other wire will make this triangle to point P. So RP is 10 centimeters or 0.1 meters, and QP is 6 centimeters or 0.06 meters. So I had a little mistake there. I put 0.6 meters, which would be 60 centimeters. This should be 0.06. Fix that really quick. Okay, so 0.06 meters for the distance QP. So in order to find the magnetic field at this point, as well as the angle, so the magnitude and the angle, we first need to find the angles theta 1 and theta 2. Okay, so to find theta 1 and theta 2, we can use our law of cosines, which says that the cosine of the angle, theta 1 here, is going to be equal to the distance of the longest side, QR, squared, plus the distance, RP squared, minus the distance from Q to P, squared, divided by 2 times the distance QR times the distance RP. Okay, and the reason that RP is the added value and QP is the minus value is because we're trying to find the angle theta 1. So for theta 2, that's going to reverse. But what we find here is theta 1 is equal to the inverse cosine of this relationship. So I went ahead and plugged the values into this relationship, and I found that it is equal to 0.896. So this is the inverse cosine of 0.896. So plugging those values into, taking the inverse cosine of 0.896, we find that this is equal to 26.3 degrees, which we can box in as our solution for theta 1. Okay, now we're going to do the similar thing for theta 2, where the cosine of theta 2 is equal to a similar relationship, or in other words, theta 2 is equal to the inverse cosine of that relationship. So again, using the law of cosines, we know that this relationship is going to be QR squared, the distance between the two wires, plus, this time it's going to be plus QP, the distance from point Q to point P on that graph back there, squared, minus the distance from R to P squared. And this is all going to be divided by 2 times QR times QP. So plugging those values into this expression and taking the inverse cosine of that value, we find that theta 2 is equal to 47.7 degrees. So now that we know theta 1 and theta 2, we can find vector B1 and vector B2, since we're going to need these values. But first, let's find the magnitude of B1. So the magnitude of the magnetic field coming from point 1 at point P is mu naught, which is the magnetic permeability of free space. This is 4 pi times 10 to the minus 7 newtons per ampere squared. It's a very common constant, especially when used when calculating magnetic fields or electric fields, and you can look that up to find out more about it. So it's mu naught times the current, I, divided by 2 pi times the distance here, which would be RP. So we plug these values into this expression, and we find the magnetic field's magnitude for 1 is 7 times 10 to the minus 5 Tesla. Okay, now we can do the same thing for B2. It's also going to be mu naught times I over 2 pi, but this time the distance here isn't r times or rp. This distance here is qp. So plugging those values in, we get a magnitude of the magnetic field from point 2, where the second wire, is 11.7 times 10 to the minus 5 Tesla. So to get the magnitude and direction of the total magnetic field, what we need to do is we need to add, so the total magnetic field is a vector, right? We need to add vector B1 to vector B2. So this is why we found the angles, because we're going to use those in these vectors. So vector B1 is simply B1. It's going to be the common thing, so I'm going to pull it out, times the cosine of the angle theta 1, and this determines our x hat direction, plus the sine of the angle theta 1, and this is our y hat direction. So that is our vector B1. So I just pulled the magnitude of B1 out because that magnitude would get multiplied by the cosine of theta 1 and by the sine of theta 1. So now, how about our vector B2? So I'm going to pull the magnitude B2 out front because it gets multiplied by both terms. And this is going to be the cosine of the angle theta 2, and this determines our x hat direction, plus the sine of angle theta 2, y hat direction. So remember, with vectors, that's theta 2, y hat. So remember, with vectors, you can only add like components. So only the x hat and the y hat components can get added together. You can't add an x hat component to a y hat component. So we plug in our values for B1 and our value for theta 1 and theta 2, and we find that this is equal to 1.58 times 10 to the minus 5 Tesla. And this is our x hat direction, plus 11.7 times 10 to the minus 5 Tesla. And this is our y hat direction. Oh, and I forgot my units on the previous one. So maybe, actually, what we can do, since they both have the same units, why don't we just put the units on the outside of the parenthesis? So this is the y hat direction. And they both have units of Tesla, so I'll just put the units on the outside, Tesla. Okay, so what we just found here is our b of x and our b of y components. So b of x is the 1.58 times 10 to the minus 5, and b of y is 11.7 times 10 to the minus 5. Therefore, we can determine the magnitude of b, because the magnitude of b, using Pythagorean theorem, is simply the square root of b of x squared plus b of y squared. So we plug in our 1.58 times 10 to the minus 5 for b of x and our 11.7 times 10 to the minus 5 for b of y. And we find that the magnitude of b is 0.12 times 10 to the minus 3 Tesla. This can be rewritten as 0.12 millitesla. We can box that in as our magnitude. Next, we need to find direction. We can use our trigonometric identity that says the direction theta, or the tangent of the direction theta, is equal to b of y over b of x. Or in other words, theta is equal to the inverse tangent, tangent to the minus 1, of b of y over b of x. So we plug in those values into this expression, take the inverse tangent of it, and we find that this is equal to 82 degrees. If we go back to our problem, that would be this angle, theta, here. So that is 82 degrees above the horizontal. So we can write above the horizontal x-axis. And we can box that in as the second part of our solution to this question, and that is the final part of our answer.